Okay, welcome to 13.2 video lesson in Algebra 2. The concept here is angles and the unit circle. Okay, guys, this is a big lesson, so if you need to, go get like a little snack or some tea and some cookies or something, because this is going to be a big lesson, but it's a very important one, okay? So I will try and make it the best that we can possibly make it. So box number 1, let's talk about angles that are in standard position. Well, all of you have taken geometry before, and back in geometry, the way that you would draw an angle is you would start with a ray, and then you would start with another ray, and they'd be joined by a common vertex, and then the space between is what we would call an angle. Sometimes we'd call that angle theta, sometimes we'd call it angle A if we were talking about out here. And this angle could just kind of be floating around in space. That was back in geometry. Now, in Algebra 2, if we're going to talk about angles, we're going to talk about angles that are in standard position on a coordinate plane. So I have a coordinate plane here. This is the x value. This is the y value. And what we're going to do is we are going to put our vertex at the origin. So that's this point back in the geometry. I'm going to put it right at the origin. And then I am going to glue down the initial side of my ray right on top of the positive x-axis. So you may recall that it had an initial side, and it had a terminal side back in geometry, okay? That initial side is going to be glued down to the positive x-axis, and the terminal side is sort of free to swing around anywhere it wants in the coordinate plane. So an angle in standard position is always going to look like this. The initial side will be glued and fixed down to the positive x-axis, whereas the terminal side, which I'll use a T to describe, is free to swing around kind of like a clock, all right? So that's what it means to be an angle in standard position. Okay, now that we know what standard position means, we can talk about clockwise versus counterclockwise. On the left in blue over here, positive angles move in a counterclockwise position. The reason is because this is coordinate plane number 1, this is number 2, this is number 3, and then this is number 4. So it swings up in a positive direction if it's going counterclockwise. Negative angles move in a counterclockwise position. So they would swing down and to the left and then up and around. So again, this is coordinate 1, 2, 3, and then 4, all right? So we have to remember positive angles swing counterclockwise and negative angles swing clockwise. And it's important that you draw the arrow to indicate which direction it is going. Because notice, if I took this arrow away and I took this arrow away, I have the exact same picture. So I have no idea if I'm talking about a positive angle or a negative angle. So you have to actually include the little direction of the angle in which we are spinning so that we can discern what the heck if we're talking about positive or negative angles. Okay, box number 3 suggests how to measure an angle in standard position. So it doesn't suggest, it tells you how to do it. So I have 2 examples for you. I have A and I have B. Okay, let's look at A first. Well, this is an angle that's in standard position. I know that much. And I know that the terminal side has swung out 90 degrees because it makes a right angle here. So because my terminal side has swept out an angle of 90 degrees and it's moved in a counterclockwise position, I know that this angle is worth 90 degrees. Okay, but take a look at part B here. This angle has swept out in a negative position because it has moved in a clockwise direction. Well, I know that this much is 90 degrees, and I know that this much is 45 degrees past 90. But keep in mind that I'm moving in a negative direction. And the reason I know this is 45 degrees is because this is 2 units that way and this is 2 units that way. So that's as indicated by this point. So therefore, if I take negative 90 degrees for that first quadrant and I take another negative 45 degrees for that second quadrant, I have swept out a total of negative 135 degrees. I just got that by adding those 2 together. Make sure that you understand why this is negative, because I'm sweeping in a clockwise direction versus this one, which is positive, because I'm sweeping in a counterclockwise direction. Okay, box number 4 is a U try. What is the measure of the angle shown? Okay, and this picture looks similar to the picture in box 3, but there's a hint. The answer is not negative 135 degrees. Okay, the answer is positive 225 degrees. So how did I come up with that? All right, well, if I've swung from quadrant 1 into quadrant 2, I've gone 90. If I go all the way past quadrant 2, I've gone another 90, and then I've gone 45 degrees into quadrant number 3. So if I take my 90 there and my 90 there and then my 45 there, I can clearly see if I add those all up, I get 225 degrees. So this angle that has been swept out is a positive 225 degrees because it moves in a counterclockwise direction. Okay, in box number 5, I'm going to show you how to sketch the angles in standard position. And I kind of shrunk this box down so we could see all 4 examples at once here. So I will do these in blue for you. Okay, let's talk about 36 degrees. Well, first I'm going to draw the point on my origin and I'm going to glue my initial side down to my positive x-axis. 36 degrees is still in quadrant number 1 and it's not quite 45 degrees, so it would look something like that. That would be an angle of 36 degrees. And I would encourage you to write in there 36 degrees inside the little angle there. Okay, B, 315 degrees. Well, again, I'm going to start with my initial side glued down to the positive x-axis. And 315 degrees would put me at 45 degrees in quadrant 4 if I swung all the way around this way. So this would be an angle of 315 degrees. Negative 150 degrees. Well, okay, if it's a negative angle, I'm going to be swinging in a clockwise direction. And negative 150 is just 60 degrees more than 90. So it's like a 60-degree angle there. So it would end up looking like this. Because this is my negative 90, and then this would be my negative 60. So if I add that up, I get negative 150. You don't have to put these in there if you don't want to, but I would put negative 150 down here. I'm just showing you how I got it. Okay, then negative 320, that would be almost all the way around in a clockwise direction, but I would leave a 40-degree gap over here, so it looks something like this. I'd be going in this direction like that. Okay, because there's 360 degrees all the way around, so that would be negative 320 degrees like that. So it's very important that you draw the indication as to which way you're going, either positive or negative. Okay, in box number 6, we're going to talk about coterminal angles. And a coterminal angle is nothing more than an angle that has the same terminal side. So the best way to show you this is to give you an example of 2 angles that are called coterminal. Let's say, for example, I have 135 degrees. So this is a positive angle, and it's been swept out to 135 degrees in this direction. Well, if I drew negative 225 degrees, you would notice that if I came this way, I would end up in the exact same location in quadrant number 2. So therefore, 135 degrees and negative 225 degrees are examples of coterminal angles because they share the same terminal side. So they end up in the same exact spot. So it's important to distinguish how you want to end up in this spot. You can get there by traveling a positive 135 degrees, or you can get there by traveling a negative 225 degrees. So these are examples of coterminal angles. I wonder how many coterminal angles we can come up with. All right, ladies and gentlemen, you have finally arrived at the unit circle. Take a moment and actually appreciate the fact that this is the beginning of a whole new realm of mathematics for yourself. We use this in Algebra 2, we use this in Pre-Calculus, we use this in Calculus, we use this in Calc 2, Calc 3, Physics, and this is used everywhere. And it's so basic, yet can be so complicated at the same time. So I want to start you off on a good note, and I'm going to give you 4 basic bullet points that we need to talk about for what's called the unit circle. First of all, you should recognize that the unit circle is just a circle that has a radius of 1 unit. That's really all it is, but there's so much that comes from this thing. Okay, it's a circle. It's centered at the origin 0, 0. So you always know that this spot is the location of 0, 0. The radius is 1 unit. So from here to the edge of the circle is 1 unit. That's why they call it a unit circle. Haha. Okay, every right triangle formed by the radius has a hypotenuse of 1. What the heck does that mean? Well, that means that if I drop a perpendicular here and I go back to my origin and make a right triangle, then I'm guaranteed that the hypotenuse is 1. Obviously, since the radius is 1, the hypotenuse is going to be 1. That's not very exciting, but very useful. Okay, and here's the really cool one. Points that are on the unit circle, so I'm talking about every single x, y point that is actually on the unit circle, they are related to periodic functions. They are related to periodic functions. This is going to come in and be a huge thing for us in the next couple of units. So here are the basic facts of what a unit circle is. Before we dive any deeper, let's make sure we have these in our notes. Okay, I'm going to take you on a trip down memory lane in box number 8. So we have cosine and sine of an angle. Hopefully you remember that in geometry, when we had this right triangle thing here, that if you were given an angle, okay, and then the side that is opposite the angle is called the opposite side, and the side that is actually adjacent to the angle is the adjacent side, and of course the hypotenuse is always opposite the right angle. But hopefully you remember that the sine of any angle is equal to the opposite divided by the hypotenuse, and hopefully you remember that the cosine of any angle is equal to the adjacent divided by the hypotenuse. Okay, hopefully you remember that from geometry. Now, let's consider our very basic unit circle picture over here. I'm going to talk about this specific point right now. I'm going to call it x, comma, y. And I'm going to draw a right triangle onto my picture. That means that this distance is x, and that means that this distance is y, right? Because if I go x, I go over x, and I go up y. And then, of course, I have a hypotenuse, and oh my gosh, this picture looks exactly like that picture, where this is my angle theta. So check it out. The sine of my angle theta, according to geometry, is the opposite over hypotenuse. Well, in this case, the opposite side is the value of y, and the hypotenuse is the value of 1. So, oh my gosh, every sine theta is just worth the y value. Woo! Okay, cosine theta is the same thing. The cosine of theta, according to geometry, was the adjacent over the hypotenuse. So in this case, it's the x value divided by, oh my gosh, the value 1. So now we have just learned that every cosine is worth the x value. This is so amazing and so simple, but you have to commit this to memory. Every y value is your sine theta, every x value is your cosine theta, and that's the reason why. Okay, congratulations, you made it all the way to box number 9, and it's only been 10 minutes and 12 seconds worth of video. Okay, so box number 9, we're going to find the exact values for sine and cosine. Exact values. I'm going to show you in the next box, or in the next lesson, what I mean by exact values, but for right now, we're just looking for a non-decimal, non-repeating value, okay? So there's an easy one and there's a harder one. The harder one, we're going to do this one in class. So I need somebody to remind me to do this one in class, like for the quick start or something like that. So let's do a theta that's equal to 270 degrees. So I'm going to draw an angle in standard position that's equal to 270 degrees. Well, that puts me right here. And if I was on the unit circle, that point that corresponds to it would be the point 0, -1. The 0 is the x value, and the -1 is the y value. And we just learned in the previous box that the sine of any angle theta is worth the y value, and the cosine of any angle theta is worth the x. So it must be true then that the sine of my angle, which is 270 degrees, is just the y value, which in this case is worth -1. Woohoo! So the exact value for the sine of 270 is worth -1. What about cosine? The cosine of 270 degrees is going to be the x value at that point, which in this case is just worth 0. So this is where we're going to learn how to do exact values around the entire unit circle, but I wanted to start with an easy one. We'll do the harder one in class tomorrow. All right, thanks for hanging in there.